The orbital period is the time taken for a given object to make one complete orbit around another object. When mentioned without further qualification in astronomy, this refers to the sidereal period of an astronomical object, which is calculated with respect to the stars. There are several kinds of orbital periods for objects around the Sun. The sidereal period is the temporal cycle that it takes an object to make a full orbit, relative to the stars. This is the orbital period in an inertial frame of reference. The synodic period is the temporal interval that it takes for an object to reappear at the same point in relation to two or more other objects. For example, when the Moon relative to the Sun is observed from Earth returns to the same illumination phase. The synodic period is the time that elapses between two successive conjunctions with the Sun-Earth line in the same linear order. The synodic period differs from the sidereal period due to the Earth's orbiting around the Sun. The draconitic period, or draconic period, is the time that elapses between two passages of the object through its ascending node, the point of its orbit where it crosses the ecliptic from the southern to the northern hemisphere. This period differs from the sidereal period because both the orbital plane of the object and the plane of the ecliptic precess with respect to the fixed stars, so their intersection, the line of nodes, also precesses with respect to the fixed stars. Although the plane of the ecliptic is often held fixed at the position it occupied at a specific epoch, the orbital plane of the object still precesses, causing the draconitic period to differ from the sidereal period. The anomalistic period is the time that elapses between two passages of an object at its periapsis, the point of its closest approach to the attracting body. It differs from the sidereal period because the object's semi-major axis typically advances slowly. Also, the Earth's tropical period is the time that elapses between two alignments of its axis of rotation with the Sun, also viewed as two passages of the object at right ascension 0. One Earth year has a slightly shorter interval than the solar orbit because the inclined axis and equatorial plane slowly precesses, realigning before orbit completes with an interval equal to the inverse of the precession cycle. Relation between the sidereal and synodic periods. Table of synodic periods in the Solar System, relative to Earth. In the case of a planet's moon, the synodic period usually means the Sun's synodic period, namely, the time it takes the Moon to complete its illumination phases, completing the solar phases for an astronomer on the planet's surface. The Earth's motion does not determine this value for other planets because an Earth observer is not orbited by the moons in question. For example, Deimos' synodic period is January 26, 48 days, 0.18% longer than Deimos' sidereal period of January 26, 24 AD. Calculation. Small body orbiting a central body. According to Kepler's third law, the orbital period of two bodies orbiting each other in a circular or elliptic orbit is where is the orbit's semi-major axis, typically in kilometers, is the standard gravitational parameter, typically in is the gravitational constant, is the mass of the more massive body. For all ellipses with a given semi-major axis the orbital period is the same, regardless of eccentricity. Orbital period is a function of central body's density. When a very small body is in a circular orbit barely above the surface of a sphere of any radius and mean density I, the above equation simplifies to. So, for the Earth as the central body we get, hours, and for a body made of water, hours. Thus, as an alternative for using a very small number like g, the strength of universal gravity can be described using some reference material, like water. The orbital period for an orbit just above the surface of a spherical body of water is 3 hours and 18 minutes. Conversely, this can be used as a kind of universal unit of time if we have a unit of mass, a unit of length and a unit of density. Two bodies orbiting each other, in celestial mechanics, when both orbiting bodies' masses have to be taken into account, the orbital period can be calculated as follows. Where is the sum of the semi-major axes of the ellipses in which the centers of the bodies move, or equivalently, the semi-major axis of the ellipse in which one body moves, in the frame of reference with the other body at the origin, is the sum of the masses of the two bodies, is the gravitational constant. Note that the orbital period is independent of size. For a scale model it would be the same, when densities are the same. In a parabolic or hyperbolic trajectory, the motion is not periodic, and the duration of the full trajectory is infinite. Synodic period, when two bodies orbit a third body in different orbits, and thus different orbital periods, their respective, synodic period can be found. If the orbital periods of the two bodies around the third are called and, so that, their synodic period is given by tangential velocities at altitude, binary stars, see also, geosynchronous orbit derivation, sidereal time, sidereal year, opposition, list of periodic comets, notes. External links.